Okay, here's the last formal lesson dealing with this unit. Okay, now this you don't have on your sheet, but that's okay. These are some of the different applications that I can think of dealing with periodic functions that you might come across, depending on what you choose for your career path. Now, if this was a normal classroom, I would click on these and I'd actually would take you to places and they talk about them. So one studying, the moon, phases of the moon, obviously that's very periodic. We know what the full moon is and new moon. Another one dealing with any kind of machinery that deals with a periodic fashion, such as this. Earthquake, because we're talking about seismic activity, so people dealing with that. Music, highly related again because of sound waves. Robotics, obviously the human ear again because of sound waves. Okay, and I can't remember if this one has something or not. Okay, so lots of different applications. Now, obviously, because everyone's going into different directions when they leave high school, you only get a taste of some of these. So we don't, and because of our skill level, we can't go into a lot of depth that you would do if actually one of these was your career path. Okay, so our goal today is I can use sinusoidal functions to solve periodic situations. Okay, now there are two major types of application questions that we're going to be looking at. Okay, the first type is where a formula has been given. And usually I find that this one is easier for me personally. But the thing is that I have to be able to usually interpret the meaning of those variables in real world situations, which sometimes can be difficult, and or substitute values for the variables to solve a situation. Okay, so often if we're not given a formula, we usually are expected to come up with a formula. So and then obviously substitute values in. So this is the first type that we're going to look at. So the first one says the following describes the voltage in terms of time, where Vt is a voltage, T is the time expressed in seconds, and then it says Vt equals negative 20 sine 600t plus 99. Okay, another thing that you'll notice with real world examples, the numbers are usually larger and often they're not very nice numbers too. Okay, so first of all, I'm going to look at this. So this says voltage equals, and it looks like my time is what I'm substituting in where I usually put my angle. Okay, so first of all, it says what is the range of voltage? Okay, well, range would be if I went to graph this, what would my highest point be and what would my lowest point be? Now, notice it doesn't ask me to graph it, and I don't intend to graph it. However, I might sketch something to help me figure out what I need to know. So, in green, I'm just going to see. If I did graph it, I would start at 99. And I probably should put it on the other side because it looks like it's negative 99. So 99, and this is my amplitude. So I would go up 20, so I would add 20 to that, and I would subtract 20 to that. Okay, so that would give me then my range values. That's where my dotted lines would be. So 99 plus 20, so we're looking at 119, and minus 20, I'm looking at 79. Okay, so what is my range? Is between, so my voltage is a real number such that it needs to fit between 79 and 119. So I can write it like that, or I can put um, voltage is between 79 volts, which is V, to 119 volts. Either way would be acceptable for a word question. The next thing it asks me, what is the voltage at 12 seconds? So they've given me time. So that means T equals 12 if T stands for second. So I need to go back and see. It says T is in seconds, so I'm fine. Because I want to check that, because what if they said, what is the voltage at 1 minute? Well, my formula is not for minutes. My formula is for seconds. So all we're going to do here is we're actually finding V at T. So this is from one of our earlier units. Negative 20 sine 600 times 12 plus 99. Now, really important that you're taking the sine of this angle, not just of 600. So you might want to, depending on your calculator, you might want to actually calculate this angle first of all. So 12 times 6, so we're looking at 7,200 plus 99. Now, obviously, I'm going to bring out a calculator. I'm going to make sure that I'm set on degrees. And amazingly, I have a graphing calculator just lying around on my computer. Okay, so I'm going to clear whatever I had there. So I have negative 20 times the sine of 7,200. I'm going to close the bracket because I don't trust calculators. And I get 99. So that means actually I am actually right in the middle of my graph. Okay, so what is the voltage? The voltage is 99 volts. It then says, how long is one cycle? Well, remember, we didn't draw this, so I'm not quite sure. Well, remember a cycle, and this is from our first kind of lesson, a cycle is the same as a period. So I do know things about periods and formulas because I know period is equal to 360 divided by B. Now in this case, my B, if I go back up to my equation, is 600. So when I substitute 600 in here, and again, I have to reduce that because it's not in lowest terms. Now I've seen some textbooks that leave it like that. I really don't particularly like that. So obviously 10 goes in each one, 6 goes into 36 6 times, and it goes into 60. 10 times, I'm still not done. It goes, so we go 3/5. So how long is the cycle? The cycle is now 3/5. 3/5 what? Okay, if we went to graph that, what is that? What's along the x-axis? Well, the x-axis is where the t is, so that would be seconds. So it is repeating it every 3/5 of a second. Okay, so that's probably not something that we could measure. Okay, so let's look at the next question. Okay, so type 2, situations given. Okay, usually they ask you, must make the graph using the information given, then use the graph to make the equation, and then you use the equation to answer the questions. Okay, so that's usually typical of this. So here's one example. Often you'll see ones dealing with Ferris wheels because it goes around. I've seen it with tides, high tide, low tide. Okay, very similar stuff. So the wheel has a radius of 9 meters, is 1 meter off the ground, and makes one revolution in 12 seconds. So it's going pretty fast. So it says graph Ryan's height in respect to time for 2 complete revolutions with Ryan starting at the lowest point of the Ferris wheel. Okay, so the first thing I need to do is I need to sketch the situation and then add the graph. Okay, so I know that I have a Ferris wheel. Okay, I know it's a wheel. Okay, so I have this wheel. Get my pen up here. I have this wheel. And I know that it's so far off the ground, so I'm not to scale. Okay, so here's my wheel. Now, what do I know about this wheel? Well, I know a few different things, and actually I'm going to make mine just a little bit larger. I don't know what I was thinking. Okay, so I know it's 1 meter off. So I'm just going to put in those numbers just on my diagram. So on my diagram, I have 1 meter, and then that's at the bottom of the wheel. Then I know that my Ferris wheel has a radius of 9. So when I get to the top here, this is 9. So 9 plus 1, so I'm at 10. And then I go another 9. So now the top, I'm 19 meters off the ground. Okay, so that is kind of making my diagram. I know it's kind of crappy, but what do you expect from a math teacher? All right, so the first thing I'm going to do is I'm going to draw my ground. There's my ground. Okay, and I know the next that I have to have a y-axis. Okay, and what I'm going to do too is I'm just going to superimpose my dotted lines just like this. Now, as I said, obviously I'm not to scale because this is not 1. So I'm just going to go something like this just so that you know that I didn't start in the right spot. Okay, so I already know on this graph, move that one down a little bit, that um, this is 1, this is 10, and this is 19. Okay, the next thing I'm going to look at next is it says 1 meter up, 9 up from 1 and another 9. We did that. Then it says period equals 12. Sinusoidal has 4 sections. What the heck does that mean? Well, I'm going to draw Ryan's height, his actual graph, and I'm going to choose red. It tells me he starts at the bottom, and I know that a sinusoidal will go like this, right? So this is one complete revolution, okay? And when I'm talking about 4 sections here, do you notice there's a section from 0 to here? 1, 2, 3, 4. Now those are even sections, and I know my period is 12. So if I take 12 and I divide it by 4, I end up with 3. So each one of those is occurring at 3 seconds. So that's the first thing I'll do. So this is 0. This would be 3, 6, 9, 12. Now the question asks me to do it for 2 complete revolutions. He's going around there twice. So add another 3, so I'm at 15, 18, 21, and 24. Okay, so I'm just going to complete the rest of my dots. All right, so there we have 2 complete revolutions graphed, and it actually wasn't too bad doing it that way. Okay, now obviously we don't want the graph to go into the negative because we're not going back in time. Okay, so let's see what we need to do next with this question. It then says, write an equation that models the situation. So when I'm doing that, I need to calculate the values for A, B, C, and D. Okay, so I'm going to write those down and we're going to go back and then make our equation. Okay, so let's look at our amplitude. Our amplitude is half the distance of our graph. Well, that is the radius of our circle, so that's 9. Our B value, well, this one we have to calculate. Remember, B is related to the period. I know my period's 12, so my B is going to equal, oops, sorry about that, is going to equal 360 divided by 12, which we know is going to be 30. My C value is where is the middle of the graph? Well, the middle of the graph we've already calculated is 10. Oops, sorry. Middle of my graph is D, which is 10. And my C is my phase shift, and I have to determine whether I'm going to use sine or cos. So I'm going to stop the video because I'm running out of time, and we'll just finish this question up then.